In this image, I've depicted one of the classic types of plate boundary that we have in our plate tectonics theory, and it's where oceanic crust is thrusting beneath continental crust, where we have the subducting crust melting, turning into magma that can express itself as volcanoes in areas such as the Andes Mountains in South America or the Cascade Mountain Range in northwestern United States. So this would be the type of plate boundary that would be present in both of those locations. We'll get into more of these details in this chapter. Why we're considering this topic in an environmental geology class is because some environmental issues and concepts can be put into a plate tectonics construct. So if we can understand why it might be better to use certain portions of Earth's surface for different purposes based on our understanding of the plate tectonic conditions. When looking at the internal structure of the Earth, we need to recognize that Earth is a layered and dynamic system with interior differentiation and concentric layers. So there are different zones or layers within the Earth. A chemical model of composition of Earth might recognize the density of the material, and we recognize that the crust is on the outside because it's lighter, and the mantle is next in density, so it's next in as we go deeper. And then we get to the heaviest materials and we get to the core. And we also introduce the concept of the Moho discontinuity as the boundary between the crust and the mantle. A physical property model would recognize that those different layers have different physical characteristics. The outer crust is a solid. The mantle is largely, or best interpreted as a liquid. Some are stronger, some of these layers are weaker. The lithosphere is the crust and the upper rigid mantle, and the asthenosphere is the next layer down, followed by the mesosphere, the liquid outer core, and finally the inner solid core. One way to try and understand how it is that Earth developed in these different layers from what was once a fairly uniform blob is, I like to use the analogy that comes from a very different context, but imagine what would happen, and this is an analogy for 21 and older. Imagine what would happen if you had a bunch of cans of beer and a bunch of cans of Coke, and you mix them up in ice, and so you have only ice, cans of Coke, and cans of beer, and you mix them thoroughly so that they're in a random collection in your cooler, and then you don't drink any beer, don't drink any Cokes, just let them settle. See what happens as the ice melts. What you'll find is that as enough ice melts, the Coke and the Cokes become mobile. They are more dense than water because they contain sugar, so they're going to sink to the bottom of the cooler. The beer, which contains alcohol, is lighter than water, so as it becomes mobile, it's going to rise to the top of the cooler. So there we have a density differentiation of the different layers, and believe it or not, it's really fundamentally the same process that allow these different types of composition to define the different boundaries. The lighter crust materials, what's accumulated at the surface, and the heaviest materials are liquid. The heaviest materials are iron and nickel, and they've accumulated at the inner solid core of the Earth. Seismology is the study of earthquakes and seismic waves, and by looking at how waves pass through different layers of Earth, we can infer properties for those layers. So by examining the paths and the speeds of seismic waves and the reflection and refraction of waves, we get an understanding of what the different layers are composed of in terms of their physical properties, and then we can infer their chemical properties. Magma is likely generated in the asthenosphere, which is some of the outer portions of Earth's mantle. And Some slabs of lithosphere crustal material have apparently sunk fairly deep in the mantle based on how we understand some of seismic waves being interrupted by chunks of lithosphere in the mantle. There's also a significant variability of lithosphere's thickness that reflects its change in its age and history. More about seismic waves and the internal structures of Earth. Earth's interior boundaries involve sudden changes or inferred from sudden changes in the speed of seismic waves. Some of the different characteristics are known to us because of the different rates and paths of wave propagation. The asthenosphere is a low velocity zone. It's where the crust is melting as it's thrust down into the mantle. And it's a low velocity zone for seismic waves, and it's a major source of Earth's magma, which we know which come up to the surface on occasion due to volcanic eruptions. When we look at the outer core of Earth's interior, so we're getting down into fairly deep layers, we find that the outer core is liquid and the inner core is fairly solid. Because the outer core is liquid, we find that no S wave transmits through it, but S waves can transmit through the inner core. Earth's interior, and with the relative thickness of each of the layers depicted here. When we look at the internal dynamics of Earth, we see some evidence for our understanding of its internal structure. One is Earth's landscape. Why do we have mountain ranges in some areas? Why do we have ranges that are roughly aligned or form a line across the edge of a continent? Why are there volcanic island arcs in a number of different locations across Earth? Those kind of landscape features help us gain an understanding. Why do we have earthquakes and volcanoes in some areas but not in others? Plate tectonics is initially a hypothesis and developed into a theory that's fairly well accepted that emerged from some important concepts that we're going to look at closely. The first is continental drift, then seafloor spreading, then plate tectonics as a unifying theory. Plate tectonics was not a well-accepted concept in the United States when I was born, but by the time I was studying anything in geology, it was well accepted, and accepted to the point that it was always hard for me to imagine what could have come before plate tectonics, and it still is hard for me to imagine what thinking was before plate tectonics was introduced as a hypothesis. So first we look at the dynamic Earth. Some of our evidence are mountain belts, continental mountain ranges, and oceanic ridges that we know are present. We have earthquake distribution zones. We have concentrations, for example, in the Pacific Rim, where we know that there are an abundance of earthquakes. We can have earthquake occurrence over time. We have a certain cycle of expected earthquakes in Southern California, and a different cycle of expected earthquakes in an area such as southeast Missouri. We have volcanism occurring in particular locations. Volcanoes don't just erupt anywhere. They tend to be concentrated in particular locations. And when we look at volcanism over time, some volcanoes are fairly active, and some are ancient volcanoes no longer active. He proposed the idea. The concept that was first introduced is that fairly recently, at one point in Earth's past, there existed Pangaea, where all continental crust, all land, was unified into a supercontinent for some time. You see that depicted in the upper left image shown here. Then, as Pangaea began to break apart, it was two different continents were created, Laurasia and Gondwana. And Pangaea began separating or drifting apart about 200 million years ago, and Earth has been evolving since. Australia were once connected in Gondwana land, um, and India, are that we have a number of fossil bands that span these different continents that give us a clue to how the puzzle pieces were once put back together to form Gondwana land. We might also look at rock distribution uh, that was subjected to Paleozoic glaciation, and we believe that a single cycle of glaciation affected rocks in everywhere from South America, Africa, India, Australia, and Antarctica. Next, we can look at seafloor spreading. In the early days of understanding continental drift, we lacked a mechanism for why the continents were moving. But then in the 1950s and early 1960s, we began to have oceanic expeditions, which increased our understanding of oceanography. Finally, in the 60s, Harry Hess proposed seafloor spreading, which recognized that the seafloor is not a single static piece, that helped us understand that there were mid-ocean ridges or spreading centers where new crust was being formed. And these sites became the driving process for why continents are moving apart in something of a conveyor belt, and they're being driven by the process that's occurring at the seafloor spreading centers, where magma is emerging, creating new continental crust, and that energy is what drives the earlier layers of oceanic crust to move apart, to move away from the spreading center. Data map. This would recognize that we have a dipolar magnetic field that sometimes north on a compass would be north, but at other periods of Earth's past, north on the compass would have been south, so that we've had polar reversals at some points in the past. The magnetic field is recorded by iron-bearing minerals in igneous rocks. Not all minerals have the potential to create basically a time capsule of what the Earth's magnetic field looked like at the time that rock was formed, but some minerals do, and those that contain iron are the ones most likely to. And what this paleomagnetic data reveals is that there were some striking symmetrical magnetic anomaly stripes around seafloor spreading centers, and I'll get to that in a minute. That allows us to look at the age of seafloor rocks and recognize that we have progressively younger rock towards the center of the mid-oceanic ridge. And we also can look at the thickness of the seafloor sediments to recognize that they get progressively thinner as we move towards the ridge, so that we just haven't had a lot of sediment accumulation near the spreading center. But when we get to oceanic crust that's older, away from the spreading center, we get thicker accumulation of seafloor sediment. So here's a map of the different paleomagnetic data that allows us to identify seafloor spreading centers. And notice it's not one band, but we actually have an interrupted band where we have the band that's relatively continuous, but then it's disrupted by a transformed fault before it continues through an additional portion of the ocean. The Atlantic Ocean is the one that's most classically interpreted as a seafloor spreading center. One of the interesting things about this seafloor spreading center is that it happens to come up towards the surface in Iceland, way up here. The seafloor spreading center is at the surface, which allows us to look at what the processes are, where this basaltic oceanic crust material emerges and is created. When we put all of these concepts of seafloor spreading centers and continental drift together, we get what we get are important elements of plate tectonics. Plate tectonics is a unified theory. It allows the study of the dynamic creation, movement, and destruction processes of plates. Plates are fragments of the lithosphere, Earth's crust, and plates move in relation to one another at various rates. India is really moving fast, and other plates move much more slowly. There's no major tectonic movements within a plate, and we find that dynamic actions are concentrated along plate boundaries. Plate boundaries are defined by areas of concentrated seismic and volcanic activity, by rifts, by faults, and by mountain ridges. There are three major types of plate boundaries. There's the divergent plate boundary, where plates are moving apart and new lithosphere is being produced in mid-oceanic ridges. There are convergent plate boundaries, where plates collide and you have some subduction at many convergent boundaries, and you have some mountain building at many convergent plate boundaries. Another type of plate boundary, the last type, is the transform boundary, where two plates slide past one another. The transform faults that I was highlighting earlier in the along seafloor spreading centers is one example of transform faults, but the most common transform fault example that people use is the San Andreas Fault in California, where one part of the Earth's oceanic crust, of continental crust, is sliding along another. The mechanism for plate tectonics comes from Earth's interior convection. So the heat generated inside or existing inside Earth's interior actually provides the driving mechanism for the circulation of the relatively liquid portion of Earth's interior, and creates the magma concentrations that express themselves as seafloor spreading centers. Current interpretation of plates and plate boundaries are shown. The relative motion of one plate compared to another is shown here. Notice, for example, I talked about zone out here in California, and we also have places in South America, for example, where the Nazca plate is thrusting beneath the South American plate, resulting in a ridge of mountains along the western edge of South America called the Andes. Well, if you look at northwestern United States, we have a similar geometry behind what creates the Cascades range in Washington and Oregon. So we tend to have these fairly consistent types of boundaries across the Earth. We have relatively stable continents, such as in Australia. It isn't a lot of tectonic activity. There are no interior plate boundaries in Australia, and the rocks are very old. You can look at one of the youngest mountain ranges, and it develops right here in the Himalayas, where the land that forms India has been thrust up into the Eurasian plate, and the collision of two continental plates has created a very huge mountain range, and it's a very young mountain range. We're going to focus on some of these details for the different plate boundaries next. In Table 2.1, you have very concentrated amount of knowledge here, where it looks at divergent and convergent plate boundaries and looks at some of the plates that would be involved, the dynamic processes happening at those plates, and what that type of boundary results in. For example, a divergent plate boundary is usually oceanic and it involves two plates moving apart, resulting in a mid-oceanic ridge. An example would be the mid-Atlantic ridge. A convergent plate boundary would be where you have ocean subducting beneath continental crust. Why is it that oceanic crust always subducts below the continental crust? Because the oceanic crust is more dense. The continental crust is lighter. So like ice would want to rise to the top of a glass of water, continental crust, being less dense, is going to rise up above the oceanic crust that's thrust beneath it. Some dynamics here is that the oceanic plate sinks beneath the continental plate, that a mountain range develops on the continental side and a subduction zone on the oceanic side. You'll have earthquakes and volcanic activity associated with those. And here are some examples. And it shows the Cascade Range here and the Andes Mountain of South America have a very similar process there. Table 2.1 continues on the next slide. I spend a lot of time looking at Table 2.1 to understand these processes. I'll talk about them on the next slide. At divergent plate boundaries, plates are moving away from each other. The most common example of this is the mid-oceanic ridge. We have occasionally some continental rift valleys. One example of continental rift valley is found in Africa. Another is the Rio Grande Valley in New Mexico is perceived as attempted continental rift that just never succeeded. At active divergent plate boundaries, we have new seafloor being created. We have extensional stresses where the crust is being pulled apart, and we have relatively shallow earthquakes. And the type of volcanism we have at divergent plate boundaries is always basaltic volcanism. We always get basalt as a result of this magma extrusion coming up to the surface. The next type of plate boundary is I'm putting all types of convergent plate boundaries together here. We have plates colliding at convergence, where the plates are converging or coming together, so they're colliding. We have a CC, a CO, and OO boundary type. The CC, or continent to continent, we have major young mountain belts being built and relatively shallow earthquakes. The Himalayas are an example of a relatively young mountain belt. But we've had some continent-to-continent boundaries in the past. We're kind of in one because the Appalachian Mountains are believed to be a case where once two continents collided, created this continent-to-continent boundary that healed and aged. And so our mountains in the Appalachians aren't as high as those in the Himalayas. They've been worn down by age. The next type of convergent plate boundary is the CO boundary, where we have major volcanic mountain belts, subduction zones, and an oceanic trench, and earthquakes associated with these. So we have this kind of boundary along the western edge of South America, and up in the Andes Mountains, and in many other locations on Earth's surface. There's another type of convergent plate boundary, and that's the OO boundary, where we have oceanic crust and oceanic crust. Now here, it's something of a competition. Which oceanic crust is going to be subducted beneath the other? It's not always clear, because they both have similar density. This leads to some very deep subduction zones that are deep oceanic trenches. We have some, for example, in the South Pacific. We often have a volcanic island arc on the side of the ocean that is not subducting, and we have a much broader or wider earthquake zones because these can become so deep that we tend to have a broader amount of the crust involved in this type of plate boundary. Two plates slide past one another. Uh, Along the spreading zone is not a single continuous rift, as we saw when we looked at the paleomagnetic data, that we have some locations where it's offset, and those offsets are transform faults. Most transform plate boundaries are within oceanic crust, but some occur within continental crust, and the most famous transform plate boundary on land is the San Andreas Fault in California. This is a depiction of oceanic crust subducting beneath continental crust. This would be an example of the examples of these would include the creation of the Andes Mountains in South America or the Cascade Range in northwest United States. This slide also depicts a transformed fault where we see the spreading center being disrupted on location. So it looks like the spreading center. So here's the spreading center, and then you see a disruption in it before it continues as you move further along the plate. So plates move fairly slowly. In fact, they move just a few centimeters per year, which is about the same growth rate as for a human fingernail, just to help you put it in context. These rates of movement do change over time. An example of the type of plate movement that you might expect is the San Andreas Fault is estimated to move at about 3.5 centimeters per year. When there are rough edges along the plate boundary, they tend to, when those boundaries move quickly, then you're likely to have an earthquake form. But for other plate boundaries, it's a more gradual movement, and so you get what's called a creeping movement. And if there are earthquakes, they tend to be of lower magnitude. We do see some changes in the movement of a plate, and we'll be talking about an example of this in a few minutes. And that brings us to hotspots. Hotspots are not along plate boundaries, but they're another feature within plate tectonics that require us to explore further and find an understanding of how they exist. These are what a hotspot is. It's a volcanic center where you have a magma source that's deep within the mantle, perhaps near the core mantle boundary. We're not sure. But hotspots can be on continents or on oceans, and the two most prominent examples for those of us who live in the United States would be Yellowstone and Hawaii. Both result from hotspots. But those aren't the only ones that we can find traces of in the United States, but those are the most well-known. A hotspot can form a chain of volcanoes over a stationary hotspot. It's actually the plate that drags across this one fairly stationary hotspot, and as a result of the plate dragging over it, the volcanic activity produces a chain of islands as the hotspot activity continues while the plate moves along on its way. This is why we have a string of islands in the Hawaiian Islands, and the Hawaiian Islands are just the most recent expression of this volcanic activity. There are seamounts that are just mountains that don't penetrate the top of the ocean surface that constitute the Emperor Chain. So when we combine those with the Hawaiian Islands, we have the Hawaiian Emperor Chain in the Pacific Ocean. It's interesting that in that chain we actually see a bend in that chain over a hotspot. A bend in that chain, helping us understand that there's been a change in the plate motion when we see that bend. I'll show you that in a second. That chain of islands or seamounts that constitute the Hawaiian Emperor, Hawaiian Islands, Hawaiian Ridge, and Emperor Seamounts. And this is just a sequence of volcano or the remnant volcanic activity as one single hotspot created islands or seamounts as the plate dragged across it. The most recent the most recent volcanoes are the only ones that still form islands, and this might help you understand. So when you look at this chain, where are the youngest ones? The youngest ones are to the bottom right. Those are the most recent. When you look at the chain of Hawaiian Islands again, you'll never wonder which one's older and which one's younger. If you move to the southeast, you'll get to the younger ones. If you move to the northwest, those are the older ones, all produced from the same hotspot, but the volcanic activity has stayed in the same plate as the plate drags across that spot. Next, we'd like to look at plate tectonics and relate it to environmental geology. Why do we need to have an understanding of plate tectonics to study environmental geology? Well, a lot of when we look globally at resources, oil and gas, a number of mineral deposits, they're only in locations that depend on the relative position within a plate. So some mineral deposits are near plate boundaries, and many have to be far away from plate boundaries. Oil and gas tends to be less common near a plate, are related to the location of plate boundaries. Another reason why we need to know plate tectonics is to understand the global belts of earthquakes and volcanic activity. When we look at either of those, volcanoes or earthquakes, they tend to be associated with boundaries of plates, and they're not very commonly in the center of a plate. They tend to be on the plate boundaries. Plate tectonics also has an impact on understanding an area or region's landscape and also global climates. It's helpful for us to understand how climates in the past may have been related to the location of continents in the past when we look at the geologic record. Lastly, geologic knowledge on plate boundaries is the foundation that we use for urban development and hazard mitigation. It's why it's really important to have a seismic hazard analysis available for a city like Seattle. And it's less important for us to have seismic safety hazard mitigation available for a city like Chicago. There are fewer earthquakes in Chicago than there are in Seattle, simply as a result of the proximity to plate boundaries. This map illustrates the association of volcanic activity and earthquakes with plate boundaries. This is a record of volcanoes shown in red and earthquakes shown as blue dots across Earth's surface. And one thing that you'll notice is that the volcanic activity and earthquakes tend to be closely aligned with the plate boundaries that we were considering a few slides ago. We do have some earthquakes and a few volcanoes that aren't on plate boundaries, but they tend to be far more prominent on plate boundaries, as this record indicates. That's it for Chapter 2.